work done by the applied force change if the load is double?
How does the answer for the work done by the applied force change if the load is double? Now, actually, they are referring to the previous question here, right? The previous question. So the previous question, the force that is acting on the load now is actually the frictional force. But this frictional force actually depends on the normal reaction. The frictional force here depends on the normal reaction. It is the coefficient of friction multiplied with the normal reaction. Now, if the load is mg, right, mg, so the frictional force is mu times mg. The work done is frictional force times the distance. So it's mu mg times the distance. Now, when the load is double, right? The load is double means it will affect the normal reaction. The normal reaction is no longer mg, but the normal reaction is 2mg, double also. So if the normal reaction is double, the frictional force will also be double. You see the frictional force is the mu times the normal reaction. Okay, so when the load is double, normal reaction is double, the frictional force is also double. When we want to find the work done, we actually use the frictional force multiplied with the distance. The distance remains the same, but the frictional force now is double, 2. So the work done will also be double. So this is the answer. The work done is double. Now, why the work done is twice the original work done? Because the load is double. The load is double means the normal reaction double. Normal reaction double means the frictional force is double. If the frictional force is double, the work done against the frictional force is also double. Okay, so you can argue it that way. One depends on the other. Frictional force depends on the normal reaction. Work done depends on the frictional force. You read this exercise 5.1.
Suppose the man is pushing the same 50 kg sled down across level terrain with a force of 50 Newton. If he does 4 times 10 to the power 2 joule of work of the sled while exerting the force horizontally, through what distance must he have pushed it? If he exerts the same force at an angle of 45 degrees with respect to the horizontal and moves the sled through the same distance, how much work does he do on the sled?
For this question, we use the same formula. We substitute whatever we know into the equation, and whatever unknown is inside the equation, we can solve for that unknown. Right? So the first case, if he does 4 times 10 to the power of 2 joule of work while exerting the force horizontally, what distance must he have pushed it? Now, in the first case, the applied force is horizontal. The distance is not known. But because the horizontal, the force and the direction of displacement is the same, we can multiply them together to find the work done. So whatever that is known, the force 50 newtons, distance don't know, work done 400 joule. Okay, we are going to link up these three quantities using the formula W equals to Fd. The value of W is 400, from the above is 400. The force is 50, also given. Distance moved, don't know, so we leave it as D. Solving this equation, D is 400 divided by 50. So 400 divided by 50 is 8 meters. Right? So this is answer is 8 meters. So we make use of the same equation, W equals to Fd, substitute whatever we know into the equation, solve for the unknown. Okay. Now in the second case, if we exert the same force at an angle of 45 degrees, meaning to say the force earlier on in the first case 50 newtons, right? In the first case is 50 newtons. In the second case it is also 50 newtons. In the first case is 50 newtons. In the second case it is also 50 newtons. But this time the 50 newtons is not acting horizontally. The 50 newtons is acting at an angle of 45 degrees. So we cannot use this 50 newtons directly. We can only use the horizontal component of this 50 newtons. The horizontal component of this 50 newtons is 50 cos theta. Okay, so the horizontal component, the component that we are going to apply to find the work done, is F cos theta. F is 50, theta is 45 degrees. Right? So the distance moved through is same, right? Why is same? They told us it's the same. They told us it's the same. If we exert the same force but at an angle of 45 degrees with respect to the horizontal and move the sled through the same distance. So through the same distance means 8 meters, same as the earlier case. So we have here 8 meters, right? And if you want to find the work done, it will be W equals to this F times the D, right? So W equals to F cos theta times D. Okay, how much is it? 50 cos 45 times the 8 here. Okay. So answer is 283.
280.
Yeah, correct. So the only thing they change is angle only lah, whether it is horizontal or whether it's an angle. Horizontal you use the full force, at an angle you use the force cos theta, right? Why cos and not sine? Because this angle is the adjacent, right? No, sorry, yeah, adjacent. So adjacent you always use the cos. The force is next to the angle. This force is next to the angle 45 degrees. So you use cos. But if the force is like that, the angle is here, there's no angle here. So this component is not cos anymore. The one which has no angle one is f sine theta. This component is f sine theta. F sine theta. Okay. With adjacent to the angle, that means next to the angle, is cos theta. Not next to the angle, there's a gap between the angle and the component, then we use sine theta. Okay. So that's how we know is cos theta and sine theta. So you just say you use the full force or the force cos theta, that's all, right? Not difficult. Okay, now we are going to look at how the frictional force arrives. Even with a razor blade, which is supposed to be very smooth, very thin, there is still friction, but less friction, right? So how does this frictional force between two surfaces exist, right? So you read what is given in the textbook here to see how.
Consider a metal block sliding over a metal surface. Microscopic teeth in the block encounters equally microscopic irregularities in the underlying surface. Pressing against each other, the teeth deform, get hot, and wheel to the opposite surface. Work must be done breaking these temporary bonds, and that comes at the expense of energy motion of the block. To be discussed in the next section, the energy lost by a block goes into heating both the block and its environment with some energy converted to.
So what they're trying to say is that whenever there is a frictional force, energy is used up. This energy is used up as heat energy, because when you rub two surfaces together, right, the two surfaces become very hot, and the work done is the energy is converted into heat energy. Let's say I pull a block along the surface of the floor, and after some times the object gets heated up, the floor also, the temperature of the floor will also increase. So why the temperature increase? The temperature increase because there's heat energy. Where does the heat energy come from? The heat energy comes from the work done. I have to pull the thing, I have to use up the work. This work is converted into heat energy. That's what they are trying to say. The work done against frictional force is actually converted into heat energy.